Hello everybody, welcome to the lecture series on EC368 Robotics Module 5. We had done Velocity Kinematics Part 1 in the previous lecture, and in this lecture we are continuing this. We are going to study an important derivation called the derivation of the Jacobian. Just a reminder once again, as this video involves a lot of derivations, a lot of symbols, please keep your notes of this topic along with you so that the derivations can be seen clearly. The Jacobian. So what is this Jacobian that we are going to derive? We have studied forward kinematics in module 4. In module 4, forward kinematics, we saw that it defines a function between the space of the Cartesian positions and orientations and the space of the joint positions. So where is the end effector? What is its orientation at the current time? You can express it in terms of the space of joint positions. That is what is called the forward kinematic equations. Now the forward kinematic equations can be used to derive the velocity kinematic relationships. Now velocity relationships are defined by the Jacobian of the function that we have obtained using forward kinematics. Okay, so the Jacobian of the forward kinematic functions defines the velocity relationships. So this is why the Jacobian is important. So it is important in an analysis and control of robot motion. It is used in many aspects of robotic manipulation. 2 or 3 of them are mentioned in this slide. It is used for planning and executing smooth trajectories, the paths through which the robot moves from one point to another, for example. Those are called the trajectories. Now to execute a smooth trajectory, plan a smooth trajectory, Jacobian matrices can be used. We have studied about singular configurations in module 4. Determining singular configurations can be done using Jacobian matrices, and the dynamic equations, which we will be studying in future lectures, the dynamic equations or the derivation of those equations also, the Jacobian matrix can be used, and many other things in the analysis and control of robot motion. Now let us start the derivation of the Jacobian, as we said, with the transformation matrix that we obtained using the forward kinematic. We had studied the DH convention for forward kinematics, and at the end of it we had got a matrix that looked like this. It's the transformation from the end effector frame, the transformation T from the end effector frame to the base frame, the end effector frame N to the base frame 0. This is a function of the joint variables of the various joints. The joint variables we know are denoted by the vector Q. Q is Q1 to Qn. Okay. So Q, as we know, is theta for a revolute joint and D for a prismatic joint. Now we know that the transformation matrix is a 4 by 4 matrix. It consists of a 3 by 3 upper portion, that is denoting the orientation, and a 3 cross 1 column vector that is denoting the position of the origin of the frame, and this is a 1 cross 3 0 vector and a scalar 1. Okay, so this denotes a transformation from the end effector frame to the base frame, and this is the end result of the forward kinematic problem solution. We had seen in part 1 of velocity kinematics that the time derivative of the rotation matrix, that is Rn0 dot, that is time derivative of the rotation matrix, can be expressed as a skew symmetric matrix of the angular velocity into the same rotation matrix. So using that result, we can write the angular velocity omega n0 of the end effector of the at the end of the manipulator as S omega n0. Look at this. S omega n0 is Rn0 dot into Rn0 transpose. Why Rn0 transpose? Because we know that rotation matrices Rn0 inverse is the same as Rn0 transpose. So from this relationship, S omega n0 is equal to Rn0 dot into Rn0 inverse, but that we can write it as Rn0 transpose. So this gives me, here is your angular velocity, this gives me the angular velocity relationship. Now the linear velocity can be written as Vn0 is equal to the time derivative of On0, that is On0 dot, the rate of change of position of the origin. Okay. Then we can write these relationships in this manner also. V and 0 can be written as JV, okay, into Q dot. That is the time derivatives of the joint variables. Omega n0 can be written as j omega again into Q dot. So we are writing the linear velocity and the angular velocity as functions of the joint velocities. Now this JV and j omega are 3 cross n matrices. N is the number of joints in the manipulator. So JV and j omega are 3 cross n matrices. We can write these two equations together to represent all the velocities. V n0 omega n0 is equal to j n0 into Q dot. Now what is j n0? J n0 is JV written on the top. This 3 cross n matrix written on the top here. And below we have this 3 cross n matrix j omega. So first we write the JV matrix and below that we write the j omega matrix. So this is 3 cross n, this is 3 cross n. So j n0 will be a 6 cross n matrix, and this matrix is called the manipulator Jacobian. So this j n0, which is a 6 cross n matrix, is a very important matrix which is called the manipulator Jacobian. Now let us derive the Jacobian. For deriving the Jacobian, let us consider it in two steps. First, we will derive j omega, which relates the angular velocity. Okay. So angular velocity of the end effector relative to the base, we want n to 0. So relative to the base is determined by expressing the angular velocity of each joint relative to the base. So take the angular velocity of each joint relative to the base and then add these together and summing these. Okay. So now the joints can be revolute, they can be prismatic. Let us consider if the ith joint is revolute, what happens? So if the ith joint is revolute, the ith joint variable Qi is actually equal to theta I. Okay, so the ith joint variable Qi is equal to theta I. Now, for the ith joint, the axis of rotation we know is one less. No, we have to write Zi minus 1. So Zi minus 1 is the axis of rotation. So omega I minus 1 is the angular velocity of link I due to rotation of joint I expressed relative to the frame OI minus 1, XI minus 1, YI minus, then ZI minus 1. So omega I minus 1 is the angular velocity of link I due to rotation of joint I. Okay, so we know the assumption when joint I moves, the link I and above it, whatever it is whatever links are there, they will move, but the links below that will not move. So the frame of link I minus 1, omega I to I minus 1 is angular velocity of link I expressed relative to the frame that is associated with link I minus 1. So again, we had seen in the previous lecture that omega can be represented as Qi dot into K, theta, because theta is the joint variable. Theta dot into K is what we learned in part 1 of the lecture series. So here our theta, we are generalizing it. So we are writing it as Qi dot into K. Now what is this K in our case? A K is that particular axis of rotation, Zi minus 1. So we are writing it as Zi I minus 1. Okay. And we are writing Qi dot into Zi I minus 1. Now if this ith joint is prismatic, then if the joint is prismatic, there is no angular velocity component that is coming when the joint I moves. Okay, so omega I to I minus 1 is equal to 0. So that makes it very simple. There is no derivation here. If the ith joint is prismatic, there is no angular velocity associated with the movement of the prismatic joint. So omega I minus 1 is equal to 0. Therefore, the overall angular velocity omega n0, the overall angular velocity with relative to the base frame, so 0, omega n0 can be written as the sum of the angular velocities of all the joints. Now we know that only if there is a revolute joint, there is an angular velocity component. If it's a prismatic joint, the component is 0. So since we want to make a generalized expression, we don't know which joint is revolute, which joint is prismatic. We are going to introduce a variable called rho I. Now rho I is equal to 1 if the joint I is revolute, and rho I is equal to 0 if the joint I is prismatic. So this takes care of this problem. Okay, so rho I is equal to 1 if the joint I is revolute. Rho I is equal to 0 if the joint I is prismatic. So now we can write the expression. So how are we going to write it? We take the first joint. So we had seen that the angular velocity is qi dot k. So we will write it as qi dot k. Alright. So this is first joint with respect to base frame. So no problem writing it like this. Since we don't know whether it is revolute or prismatic, we put this rho 1 here. If it was revolute, rho 1 will be equal to 1. So it will make it q1 dot k. If it is prismatic, rho 1 will be equal to 0. So this entire term will just disappear. It will become 0. Now going to the next joint. So you have here rho 2, q2 dot. Straight away we cannot write k. We saw in part 1 of this lecture series, we have to correspondingly transform it into the base frame by multiplying it by the rotation matrix R1, 0. And so on till we come to the nth joint, rho 1 into qn dot. You can't write k straight here. You'll have to write Rn minus 1 into R0. Just refer to the last slide of the part 1 lecture of velocity kinematics for this expression. You'll be able to understand it better. So this can be written in a compact way as sigma I equal to 1 to n rho I qi dot zi minus 1 to 0. Okay. So z00 is equal to k, that is 001 transpose. This is the k is the unit vector associated with the z axis, the base frame. Now what is this zi minus 1 to 0? That corresponds to each of these components, r into k components. So now j omega can be written. You just take out this q terms from here because we are going to write as j omega into q dot, where q is the vector of the joint variables, that is q1, q2, etc. transpose. So just take out these things. So what is left behind? I have got from here rho 1 zi minus 1 to 0. So z0 to 0, that is z0. Then next one will be rho 2 z1, all expressed with a reference to the base frame. So 0 will be there. And last one will be rho n, zn minus 1 to 0. So here also there will be a 0. We have not written that, but it is understood that is all reference to the base frame. Now let us derive the linear velocity, the component. So we want to derive jv. So the linear velocity of the end effector can be written as dou n0, dou on0 dou t. That is the time derivative of on0. Now this can be written as dou on0, okay, dou on0 by dou q into dou q by dou t. Dou on0 dou q into dou q by dou t. Dou q by dou t only we have written it as q dot. Alright, since there are n joints, we have to write I is equal to 1 to n dou n0 dou qi dot, that is dou qi by dou t. So the ith column of jv is denoted as jvi. So ith column will be dou n0 by dou qi. This is the qi dot, that vector that we had seen that we removed. So jv will be only this term. Jvi will be dou n0 by dou on0 by dou qi. Now again we have to see if the joint is revolute or prismatic. If the ith joint is prismatic, it imparts a pure translation to the end effector. So we had seen that because it imparts a pure translation, the angular velocity component was equal to 0. But here we are now considering linear velocity. So we have to check that out right now. So we can write Tn0. We had seen this in the first slide. Is written in this form. Our rotation matrix into the position vector of the origin. And this is the 0 vector. And this is 1, that is the scalar. Now we can split this into 3 matrix multiplications, Ti minus 1 to 0, Ti to I minus 1, Tni. Now in this format, we can write the 3 matrices corresponding to these 3 rotation matrices. So just see, Ti minus 1 to 0 is Ri minus 1 to 0, Oi minus 1 to 0, 0 and 1. This is a vector. Okay, so similarly these two. When you multiply these 3 matrices, alright, this is what you're going to get. So the multiplication of the matrices gives me a particular result. Now simplifying that result and making it compact, this is the final result that we are getting. Alright, so for me what is of interest here, since we are talking about linear velocity, which is on0 dot, which is on0, this is the component that is on0. So we will take out ON0. So this is ON0. This expression that we got on multiplying those three matrices, we are going to use for finding out JV. All right. So I'm bringing from the previous slide the result. I'm bringing it over here. All right. Now let us say that to simplify this derivation, let us assume that only one joint or only the joint I is allowed to move. All right. In that case, then O and I, all right, and OI minus 1 to 0 are constants. Our joint I only is going to move. So OI, I minus 1 only, this thing only is going to have a movement. So this and this are constants. Now also as the joint I is, we are considering prismatic joints, this thing also will be a constant. All right. So there is no rotation for a prismatic joint. So this I minus 1 to 0, that is up to the ith joint, that rotation matrix, that is also constant. Now we had learnt in module 5 by DH convention that in this transformation matrix that we obtained by the DH convention, the 3 cross 1 in the fourth column, the 3 cross 1 vector that denotes the origin position OI or I minus 1 is AI CI AI SI DI transpose. Please refer to module 4 notes. This result is there in the DH convention derivations. Okay. Now taking this, let us say dou ON0 by dou QI. Let us try to determine dou ON0 by dou QI is dou by dou DI. Now our joint is prismatic, so QI is actually DI for us. Now when you take the derivative, we know that this thing is a constant rotation matrix and this thing is a constant. This also is a constant. Inside this is a constant, but this thing moves. Okay. So we can write this as dou by dou di of this. Since this is a constant, this goes off, this is a constant, the derivative is 0. Okay, now only this is left. Dou by dou di of Ri minus 1, 0, this term, OI I minus 1. So this is a constant, I am taking it out of the derivative. So dou by dou di of this thing, AICI, AISI, DI. This, where did we get it from? From module 4 DH convention. All right. So Ri minus 1 to 0, when I take the derivative, this is a constant. There is no di term here. There's no di term here. So I have got the, after taking the derivative, 0 and 0. Now dou di by dou di, that is equal to 1. So I have got this also. Now dou n0 by dou t, the time derivative, which is what we want to get JV, that can be written as dou n0 by dou qi into dou qi by dou t. Okay, dou n0 by dou t is dou on0 by dou qi, which we have already got here. See, this is what we have already got. It is dou qi by dou t. Dou qi by dou t, qi is equal to d for a prismatic joint. So I can write it as di dot. So what is this component? Dou qi by dou t is this di dot. This dou on0 by dou qi I have already got here. So that is only this Ri minus 1, 0, 0, 0, 1, this term. Okay. So this can be written as di dot into zi minus 1 into 0. So this is your k that is associated with this z of the base frame. So Ri minus 1 to 0, 0, 0, 0, 1 is your z axis for the ith joint, zi minus 1 relative to the base frame. So this is your joint variable. So this is what is after the joint variable. So for your prismatic joint, JVI is equal to this component. Okay, so JVI is equal to what? The component that is the leftover after we remove the joint variable's time derivative. So JVI is equal to Zi minus 1 to 0. This 0 has to be there, but we are, even in the previous slides you would have seen that for J omega we had not written that 0. This means that I minus 1 the Z axis with reference to the base frame 0. Now, if the ith joint is revolute, bringing back that same relationship that we had taken, we had said that now we had said that in the previous case this is a constant and this is a constant and this is a constant, and we had simplified the derivation to taking this term alone. Now what happens is if the ith joint is revolute, this term is not a constant. Okay, this term Ri minus 1 to 0 is not a constant because when the ith joint moves, this rotation matrix will be changing. So since Ri minus 1 is not a constant, in the earlier case this term was a constant and this term was a constant, this term was a constant, only this was variable. Now we have this thing to be variable and this also is variable. So now you'll have these two terms coming in. So dou by dou theta I, why dou theta I? Because the joint is revolute. So instead of saying dou by dou qi, straight away we have written dou by dou theta I on0 is equal to dou by dou theta I. Now only this term is a constant, this derivative will become 0. Now these two terms derivatives we have to take. Okay. So now we are splitting it up. Dou by dou theta I of the first term, this first term, plus Ri minus 1 to 0 dou by dou theta I of this term. Okay. So now we come back to the results that we learnt in the part 1 of velocity kinematics. That what is that? If you have a dou by dou theta of r x theta is equal to s of k r k theta. Remember that? So from that relationship, we can use that relationship to do this derivative. So we can say s z minus zi minus 1. Why zi minus 1? This is the axis associated with the ith joint. So zi minus 1 to 0, ri 0, on I. So this derivative can be replaced by the skew symmetric matrix associated with a particular joint axis of rotation into that matrix. So that result from part 1 lecture we have taken here. Similarly, this also can be written like that. S of zi minus 1 to 0, ri minus 1, oi o minus 1. This one in detail I have given how this derivation comes in the notes. You can refer the notes to understand how this thing has come. So this can be written as S of zi minus 1 to 0, this term, plus ri minus 1 to 0, oi minus 1. Okay. So this can be written ri to 0, on to I is actually on with reference to the base frame 0. When I multiply on to I, okay, with on with respect to the ith frame, and I multiply it by the rotation matrix Ri with reference to the base frame, what will I get? I will get On with respect to the base frame. Similarly, we have got here OI with respect to I minus 1 frame. When I multiply it by rotation matrix I minus 1 to the base frame, what I am going to get is OI with reference to the base frame. OI with reference to the base frame. So this is the result we are getting here. The skew symmetric matrix into ON0 minus OI minus 1, 0. So continuing our derivation, dou N0 by dou Qi, that is dou theta I only we got in the previous slide. Now we are going to do that dou N0 by dou T, just like we did for angular velocity. We are going to do just like we did for the prismatic joint, we are going to do it as dou On0 by dou Qi into dou Qi by dou T. So this again is dou On0 by Qi is what for us? This is a revolute joint, so Qi is theta I into dou Qi is theta I, dou theta I by dou T. Now this dou theta I by dou T is theta dot. Okay, dou theta I by dou T is theta dot. And from the previous slide we know what this is. That is dou On0 by dou theta I is equal to S Zi minus 1 to 0 into On to 0 minus OI minus 1 with respect to 0. This can be written as theta dot into the z-axis Zi minus 1 with reference to the base frame cross On0 minus OI minus 1 to 0. So this thing can be written in this format. So now for a revolute joint, we have got JVI is equal to Zi minus 1 cross On minus OI minus 1. But this is also, like I said, with reference to the base frame. So I've got a 0 here and a 0 here and a 0 here. We are not writing it. We are just assuming when we don't write it, it is with reference to the base frame. So now we have got all the terms. So the upper half of the Jacobian JV, just now we just derived it, can be written as JV is JV1, etc. JVN. Now what is this JVI? If the joint is revolute, previous slide we had derived, no? So that if the joint is revolute, it is Zi minus 1. It's not clear here. That's why I said keep your notes here, notes right by your side. Zi minus 1 cross On minus OI minus 1. This is just the previous slide, the result that we derived. And just before that, we had derived if the joint is prismatic, the answer JVI is Zi minus 1. So the lower half of the Jacobian, that is J omega, we had done in the beginning slides, J omega 1 to J omega n, where J omega I is, if the joint is revolute, it was Zi minus 1 to 0. This is what we got. So we have written it as Zi minus 1. If the joint is prismatic, we got that J omega I as 0. So this is how we have derived the J omega and JV terms for the Jacobian. And this gives a 6 cross n matrix, which is called the manipulator Jacobian, which is extremely important in robot analysis and control. So you can see that the Jacobian function for an n-link manipulator is of the form J is equal to J1, J2, Jn. Okay. So this J1 is a combination of JV1 on the top and J omega 1 below, JV2 on the top and J omega 2 below, and so on. So we're going to write that together, where the ith column, okay, J1 or J2 or Jn, ith column Ji is given as, if the joint is revolute, JV is Zi minus 1 cross On minus Oi minus 1, and that is the JV term. And the J omega term, you remember that J omega term is Zi minus 1 for a revolute joint. Okay, so this is the JVI for a revolute joint. This is J omega I for a revolute joint. Now, if this joint, the ith joint was prismatic, then it becomes very simple. JV is equal to Zi minus 1. Okay, and J omega we had already seen is 0. So Ji, if the joint is prismatic, is simply Zi minus 1 and 0. Now, using the result of the forward kinematic equations, you can very easily find the Jacobian by finding out all these things, as we will see in some example problems in the next lecture, that is velocity kinematics part 3, and that involves a few example problems which will illustrate how the manipulator Jacobian can be derived.